All right, welcome to lecture 5. Um, this is Intro to Machine Learning 1, DS 4400, Northeastern University course. I am Professor Wu. So this is a version 2 of the lecture. I have previously recorded a different lecture for lecture 5, but since then I have upgraded it and changed the slides. So this is version 2. All right, so let's get started. We previously talked about the concept of supervised learning, and the idea is that you have some kind of data and you have some kind of result. And what you want to do is learn the model, which turns out to be a function. The way it works is you have this kind of data where each row is consists of a sample. And you want to learn a function such that when you plug the sample into x as a vector, you are able to predict the output. So that's what we're trying to do. So by having bunch of data like this, it allows us to train this model, which turns out to be a function. So what we need to do in this today is we need to discuss a little bit about the concept of preprocessing, right? It doesn't matter if you're doing like supervised, unsupervised, like any of these. When you preprocessing in general is a good idea, and what that means is sometimes you may have data that's in words instead of numbers, so we need to convert them into numbers. Other time, we want to center and scale the data. This makes sure all the data are not one particular characteristic or feature is not much bigger than the other. So you can like center it so all the dimensions have a mean of 0 and the variance of 1. Other way is to scale the data so it's always between 0 and 1. That way all the dimensions have like a same relative scale. Okay. So the first one is from categorical to number. Sometimes you or data looks like words. So over here, you have predictors, response, and this is responding whether a tennis court is going to be busy. So depending on the outlook, temperature, humidity, then you're going to have a busy or not busy tennis court. So notice these are all words. Therefore, it's going to be difficult for you to um, like mathematically calculate them. So what we like to do is to convert them into numbers. The way it will work is we just label them. Yes, for example, would be 1, no equals to 0, right? We can just automatically change that. Or the outlook category, we could have sunny to be 0, outcast equal to 1, rain equal to 2. So once we create these tables, we're able to assign numbers to each one of these. Now, this is tedious work, obviously. So, just for this particularly, I want you guys to know how to use this. Like it's called a pandas library. After you read the file, right? I print it out so you can see that I have the file. Once you have the file, you can create this thing called the encoder. With the encoder ENC, you can fit a particular dimension. So let's say we want the outlook, right? So the outlook is now like transformed as well as played in tennis. If I were to print this out, notice that the outlook has turned into numbers, so as playing tennis. So by doing this, it essentially automatically converts words into numbers for you, categories of numbers. Okay? And this is you can always transfer them back to NumPy. So now you're dealing with NumPy numbers. Okay. All right, so that's transformation from letters to numbers. Now we want to talk about center and scaling. Well, look at this number. The scale of this number is in 1, 2, 3, 4, 5, right? So these are pretty small compared to the number of square footage. Well, what happens is when you're training a model, because the number is larger, the model have tendency of saying that this must be more important. When in reality, the square footage is not necessarily more important than the bathroom. Therefore, what we normally do is make sure they're the same size. To do that, what we do is we subtract each one of them from the mean, right? So we center it, and then we divide them by the variance. So if it has a large variance like this one, after we divide them, it's going to be in the same scale. So this whole thing is to make sure that the size of each dimension is not so out of whack with each other. Okay, so so let's say we have this data. Centering is really easy. We find the average, right? We just find the average. Then we just subtract every number from the average for this dimension. So 3, the average is 2, right? So this is called 3 minus 2, 2 minus 2, 2 minus 2, 1 minus 2, like this. After that, after centering, these are the numbers. Once you have centered, now we need to scale it. The scaling follows this equation. You want to find the standard deviation. The standard deviation is basically you take this number and find the average square. So you square each one of these and then just find the average of the square. Okay? This depends on whether we're talking about population or sample. For the purpose of this class, we're going to stick with the population one. So over here, right, we just take the square of each and divide by 4. So this is the average of the square. And then the square root of that is the final solution. So this tells us that the standard deviation is 1.2. And all we do is take each number and divide by 1.2. So after we do that, it then results in this. 1 divided by 1.2, 0, 0, negative 1 divided by 1.2. Okay? All right, now let's see if you can see to find the center of. So like now we talk about column 2, right? So you got to do this for every single column when you're doing it. Well, what's the average? Well, average is just 1. And then centering, you want to subtract every number from 1, which give us this, right? You subtract everything, it gives us this. So once again, we then find the standard deviation. With the standard deviation, which is the average of the square, we then take the square root, which is once again square root of 1 over 2. So we just take each number divided by it. So the process is, let's say you have some kind of data, and the data, like here's 0, here's like 1, and over here really far away is 100, right? So the data maybe is in this range versus in this range. Notice how, let's say, the standard deviation is this big. If you were to move it to the center, so move this data to the center, so 0's here, you're going to be like this, right? And then if you divide by the standard deviation, it's going to look like this. So this is a standard size. Over here, you can do the same thing. So from 100, you can also move it back, right? After you move it back, right, then you're going to divide by the standard deviation. So all your numbers are going to be roughly in this range. That's how you end up moving the data from all over the place so that they all look like in the same scale, the same location, right? This actually drastically simplifies your training result and tends to give you better results. Now, doing this, just like converting letters and words into numbers, is really tedious. So, I don't expect you to really do this. What you do is, over here's the data. You call the function preprocessing and scale. sklearn preprocessing and scale. So this will automatically subtract the mean of each dimension and divide it by the standard deviation. Notice how this dimension is much larger, but after scaling and processing, the numbers are roughly in the same scale, right? This is like this versus this is a huge difference, but this versus this is not that big of a difference. And if I were to take the average of each dimension, you'll see that the average is 0, meaning that you've centered the data. And over here, if you find a standard deviation, you'll all be 1. That means the spread of the data is just 1. Okay? So when you're doing training, right, you if you're not getting a good result, you want to make sure you know how to do this. in general, the default is we tend to just do this anyways with any data. So scaling data between 0 and 1 over here, you want to pause the video, see if you can do it, right? Basically over here, you find the average, which is 1. You subtract every value by 1, and then you divide it by the standard deviation, okay? Oh, wait. No, this is sorry. This one is scaling the data between 0 and 1. So it doesn't matter what the number is, it's always going to be between 0 and 1. Okay. So yeah, that I was still thinking about the last one. So this particular one, what you do is how do you scale? Always make sure your data is between 0 and 1. Well, if it's over here, right, you just make sure this is 0. So you got to subtract the data by this number, right? After you subtract it, it will be something like this. You just make sure you divide it by the size of this so that it's always within 0 and 1. So I think the example I was showing you, so the minimum value is 1. So if you just subtract everything by the minimum value, that's a good start. And then you look at the range. So the range is between 0 and 3, therefore it's 2. So if you divide all the numbers by this range, then your final result will always be between 0 and 1. Okay? So this is how you scale between 0 and 1. And the way you do it is through this command, min-max scaler. Right? If you min-max scale, notice how all the numbers were previously not between 0 and 1, and now they're all between 0 and 1. Okay? So these are different ways. For image, they tend to use this a lot. And for other kind of data, in general, we tend to use centering and scaling. Okay? This this is the command that we tend to use. Okay, so now we're ready. With that, like said, we're ready to move on to the real meat of today's lecture, lecture 5, part 2. Okay, so this is a continuation from our last class, lecture 4. We previously learned about supervised learning, and with supervised learning, the goal is you have some kind of data in the label, right? And you're trying to find a function so that the difference between the function prediction and the actual truth is as small as possible. Okay, let me say that one more time. So this right here is the error square, right? Error square. So what we want is we want to find a function such that the error square on average is minimized. Okay, that's the whole goal of how we do prediction. We want the error of our prediction to be as small as possible. Now, from our last class, we said that to find a function is really, really hard because there are infinite possible functions. Therefore, what we do is we make some basic assumptions, which is we assume that the function is a combination with some kind of weighted combination of other functions, right? And once you write it this way, this implies that we can split the w's, the weights, and the functions separately and rewrite it into this compact format, right? So the function can be rewritten this way. And therefore, by finding the weights, it defines what the function is. Now, last class, we learned that, well, if we're trying to find a weight that minimizes the error, right, then the one way to do it is through this thing called the gradient descent, which you have some kind of function and you're trying to incrementally get closer and closer towards the minimum. And the way you do it is you look at your current location at time equals to 0 right now. And then you want to subtract away the derivative information because the derivative tells us whether going right or left is going to move the function down. Okay. So this right here is the gradient descent algorithm. So all you really need to know is you need to know DLDW. So if you know the gradient, you can plug it into gradient descent and then over and over again and essentially solve this problem. So that's what we learned last time. However, for this particular problem, there's a second way, which is called the closed form solution. Well, it turns out that for the mean square error objective, we can just calculate the solution directly. We don't need to run gradient descent. Gradient descent is really useful because it works for anything. But if we happen to have a regression type of problem like this, then we can just calculate directly. Okay, so it turns out that we can calculate directly, and this is based on the observation that we want to find an f of x to predict yi, right? So whatever x we put in, we want its output to be as close to the truth as possible. So in the most ideal case, we plug the first sample x1, we want to predict y1. If we plug x2, we want to predict y2, so on and so forth. Whatever sample we put in, we want to make that prediction. But given that we've defined what f is, right? We said that to simplify the problem, we're going to say f is just equal to this. So for every one of these, we can rewrite it into this form. So over here is for the first sample, the second sample, all the way to the end sample. And ideally, after we do this multiplication, the output, we want it to be as close to as possible to the truth. Okay? Now, because these W are identical, we can just pull the W out like such. We pull the W out. And once we pull the W out, we can call this matrix phi, capital Phi. So this is lowercase, this is capital. And this, now we have a really, really compact format. Capital Phi times W is equal to Y. All right, this is the compact representation. Well, once you reach this representation, if you had taken linear algebra, you would know how to solve this. There's a standard way to solve this. And let me show you how it goes. So over here, this is the problem, right? Now, we can multiply this on both sides. Okay, so they will still be equal. If you multiply the same matrix both sides, they will be equal. And now what we can do is we can multiply the inverse of this over here. So this is the inverse on both sides. So we have the inverse on both sides, here and here. They're the same thing. Well, if this is and this are inverse, right? If you have 5 times 1 over 5, that's going to give us 1. So in the matrix version, this just gives us identity. Okay? And since if W times identity is W, so basically this will equal to 1. And then we got W. So our optimal solution for W is simply this here. This tells us that as long as you can calculate the phi matrix, you can essentially follow this equation and just solve for the best fit. So before we had data that looks like this, and you wanted to find a line that best fit them. To find that line, you need to know like the weights, right? You need to know how the weights are defined. So if you can do that, all the weights, then you essentially would discover the function you're looking for. You would discover this, right? So this result implies that if we can calculate phi matrix ahead of time, so all we have to do is calculate this matrix, we can solve for W by just plugging this in. All right. If we know phi, we can just plug phi in because we know what y, we know the label. So let's look at a really quick example of what I mean. Over here is an example of a least square. So now we have these are the data. When we plug 1 into a function, we want the output to be 0. If we plug 2, we want the output to be 1. If we plug 2, we want output to be 2. Now, there's a contradiction. How can you plug the same number and get something out? Well, that means we can simply find the best possible solution that tries to satisfy them. So, in the most ideal case, we want this to equal to this, but we're going to do an approximation. So if we know that we're looking for this function that basically give us this relationship, then the first thing we have to do is to decide what the basis functions are. So we need to decide it's a combination of functions, right? So what should these functions be? The easiest one, the most commonly used, is called linear regression. Linear regression is simply saying that we're going to use two bases. That's all. The first basis is just x, right? Phi 1 of x is just equal to x. And the second one is saying that phi 2 of x is equal to 1. So this is the most basic assumption. Of course, you can pick any set of functions and combine them together. But once again, linear regression is what's used most today, like for a lot of purposes. So here it is. Now, if this is x, this is 1, then we have an equation of a line, right? We plug x here, we plug 1 here, then we got an equation of a line. So this is very useful if you have data that kind of looks like this. So what you have to do is essentially find the best equation of a line that describes the data, right? So in this case, we decided it's the equation of a line. Okay, so now that we made this decision, it is the equation of a line. What we want to do is to say that, well, we want, if we plug x1 in, it will give us y1. That's ideally the case. X2, y2, x3, y3. So ideally, this is the case. And now we write the definition of functions. So for each function, when we plug x1 in, it'll be x1, and here's the function. Over here is x2, here's the function. x3, here's the function. Okay, notice now we can pull W1, W2 out. Okay, if we pull W1 and W2 out, the result is x1, x2, x3. And this is 1. All right, try to do this multiplication in your head. Now we have achieved phi W y, right? Remember, that's what we're trying to do. Once we get to this point, then life is pretty good. Okay, so how do we construct phi, the capital Phi? Well, capital Phi, these ones is just x1, x2, x3, right? So what was that first x1? Well, x1 was this one, x2, x3. So we just plug them right here, right? Then it becomes this. Notice they're the same. Okay? And so you now have this matrix. Once you have this matrix, the solution is this. You take the transpose times itself, find the inverse, times the transpose times y. And voila, there's a solution. So this particular example, we pick linear regression. Therefore, there are only 2 bases of x and 1. But we could have done a different one, like another one that's really used often is called a polynomial regression. In this case, notice the difference. We define a bigger function. So now we have 1, 2, 3. So we have 3 functions as opposed to over here, we only have 2. And we define the first function as x squared, x and 1. Okay. So once we have this, we move them down. Then this is the function we're looking for. Something like this. So this is a function of a parabola, right? We don't know the exact parabola, but once we find W1, W3, then we know exactly which parabola will give us the least amount of error. So we follow the same procedure. Ideally, we want when we plug the first sample, we get the first y. The second sample equals to y. Third sample is equal to y3. So we plug the function in. When we plug the function in, for this function, it's for sample 1. So notice it's all x1 here. This one is all sample 2, right? We plug sample 2. So x2, x2 here. Similarly, this is x3. So if we have this, we can now reformulate this and pull out the w. So we now have w1, w2. Oh, I missed a w3. There should be a w3 here. Okay? With a w3, this means that we have the phi w equals the y equation again. How do we get phi? Well, you just plug x1 into this, right? What was x1? X1 was 1, right? So if we plug 1 in here, will be 1. 1 here will be 1. Hence 1, 1. The next one is x2. X2 is the second sample. Well, we plug in here. So x2 squared is 4, x2 is 2, and 1 is just equal to 1. Once again, we do x3, x3. So what is x3? It's also 2. So we can just copy this one. And now we have the phi matrix. So from this, I hope you come to come to the realization that it doesn't matter which bases you pick. It doesn't matter how many you have, right? You can have as many as you want, but ultimately, you just need to calculate the 5 matrix. Once you have the 5 matrix, none of these matters. All you need is this matrix. And then from this matrix, you follow this formula, then you got the weight. And that's your solution. Okay? This is essentially to give you the best possible fit of data. So I want you to take a look, like pause the video, take a look at the difference between them. Right? The only difference is the starting point. And then we construct a different phi. Once we have the phi, the equation to solve for W is identical. Okay? So for this particular example, right, that we just did, we did the linear one, right? So this is the result of phi, right? So I'm going to copy it here. And all we have to do is plug this in to this equation and we have it solved. So let's see if we can actually plug it in. Oh, by the way, y, notice this is my y. This is the y. I just copied it. Okay, that's the label. Okay, so now that we have this, for a small matrix, calculating inverse of a matrix is not that easy. It's not that easy. But for a small matrix, like 2 by 2, 2 by 2, this is definitely doable. So if you have a matrix, STUV, so this is a 2 by 2 matrix, the equation to solve for this 2 by 2 matrix is this equation here. Okay, this is how you find the inverse. Okay, well, once you have the inverse, then then you can just like plug that in here. So let's actually calculate this out. Well, first step is we want this thing here, right? Let's calculate this phi transpose phi. Okay, so if you do this, pause the video, calculate by hand, you should get this. Okay, so that's phi transpose phi. Now that you have this, we want to find it. Well, now that we have this, we want to find the inverse. So to calculate the inverse, you follow this equation, which is 9 times 3 minus 5 times 5. And when you multiply by this here, then this is the inverse. So this whole thing is simply equals to this. All right. Notice how these turn negative and these two swapped with each other. Okay, so that's the equation for it. Now that we know the inverse, we can just plug it in. So here's the inverse, which is right here. And then y, phi transpose, you just plug phi transpose in. Here's y, you plug that in. And you just calculate them out. If you calculate these out by hand or with NumPy, you should get this result, telling you that W1 and W2 is equal to this. Now, remember, we're saying that the function is linear regression, right? So it's W1 and W2. So if we plug 1.5, right, into W1 and minus 0.5 into W2, we would have the equation. So this right here is the optimal equation that does the fitting. And you can see that the first point is 1, 0, I think, and then 2, 1, and 2, 2. So it's saying that if you were to use this line, this is what give you the least amount of error. Okay, and you can see it basically picked the middle point. It split the difference. Okay. All right. So at this point, I would like you to pause the video and basically see if you can solve this. Except this time, instead of using a line, you want to use a parabola with a closed form solution. Remember, a parabola follows this equation, right? So these are the phi's, and this one is x squared. This one is x. This is 1. So in the end, you're assuming this right here is the function. So your first step is to find phi. Once you know phi, you can follow this equation here to find w. You can do this in Python. So go ahead and give this a try. I wrote the code already, but ideally you don't look at the code. Ideally, you try to run this yourself. And at the final result, notice how this is the parabola that would have given you. So it did a pretty reasonable job, I think. So you can never be perfect, but yeah, this it does the best job possible. So that's how you do the fit. So pause the video, see if you can give this a try. If you're stuck, you can look at my code. Okay, now that we're ready to move on multivariate regression. So so far we've only worked on one dimension input, one dimension output. But what if we have x1, x2, x3, x4? Actually, let's call it this way: x1, x2, x3. All right, many dimensions, and then y. All right, so you now put multiple dimension in, and you're trying to predict some kind of outcome. So that's multivariate. Well, with multivariate, let's look at an example. Let's say we're dealing with two dimension, right? So uh, for the ith, this is saying that we have a two dimension such that each sample xi is in two dimension. This symbol means such that. So it's in two dimension such that xi has two dimensions. The first dimension is xi1. Second dimension is xi2. Okay, so you can distinguish which sample and which dimension of the sample. Okay, so I put them in brackets so you know it's not power. It's not like this is to the second power or anything. It's saying that it's the second dimension of the vector. Okay, so if we're doing linear regression, the feature map, the basis functions is really simple. The basis functions is if you have two dimension, you simply say W1 times the first dimension, W2 times the second dimension, right? So you have two dimensions, you got the two dimensions. And then W3 is just times by one, which is always the case. So, so over here, let's say we have two samples, right? The first sample, X1 is 3, 2. The second sample is 1, 4, okay? So if we're trying to use a linear regression for this function, then the equation would be W1 times X1. So remember we plug X1 in. So this is the first sample, the first dimension. And there'd be W2, the first sample, the second dimension. So once you've exhausted every dimension, the very last one is always a 1. Okay, so I'm saying that the function of multiple dimension input is simply this. So each dimension has its own weight. Okay. Now, if we pull W1, W2, W3 out like this, then this is just the first sample, first dimension, first sample, second dimension, and 1. Then this is the second sample, first dimension, second sample, second dimension, and 1. Well, what are these? What's the first sample? What's the first sample, first dimension? So that's the first sample, first dimension, that's 3. And then first sample, second dimension is 2, and then 1. Over here again, this is the second sample, which is this, first dimension, which is 1, and then the second sample, second dimension, which is this. So we copy this, and then always 1 here. And there we have it. That's the 5 matrix, right? So this is how you can get the 5 matrix. And once you have the 5 matrix, you do exactly the same thing. The trick here is as long as you know which functions they are, right? As long as you know which function they are, you can always construct this 5 matrix, right? It doesn't matter how you define it. You can define this with any 5, and no matter how long, how many, which functions you pick, any you can always convert it into a 5 matrix. Once you have a 5 matrix, it's really easy now. You simply solve it this way. Now, that was the example with 2 dimension. But if you have d dimension, then basically every single dimension is going to go in there, and then a 1 for the first sample. And every single dimension is going to go 2 in there, and 1 for the second, so on and so forth. So that's what the general form of a 5 matrix will look like. Okay? All right, so that was the linear. Linear, you basically just copy the data, right? You basically copy the data and append the one. What about polynomial? Right? Polynomial of higher dimension gets much more complicated. So for the polynomial, these are the feature map. So let's say you have x well, this is, yeah, this is not good. I thought I updated this. Well, yeah, I didn't update this. So let's not look at this. I didn't. Let's say you have x I is equal to the similarly how we define it x I 1 x I 2. So what that's saying is that you have the first dimension, second dimension. So the feature map for this, like how do you map it to the phi? Well, the way you do it uh, would be this set x1. No, it'll be xi 1 square, and then xi 2 square. Okay, then you have xi 1, xi 2, and then what you have is xi 1, xi 2, and then 1. Okay, so this is this is the ith sample first dimension square, ith sample second dimension square, I sample first dimension times I sample. So these right here, right, are the feature maps. So as a result, you end up with 1, 2, 3, 4, 5, 6 dimensions. And how did I know that? Well, the way you do it is you simply take the remember the feature map. You remember the feature map for one dimension? Sorry, yeah, for one dimension linear looks like this, right? But if you have multiple dimensions, then it looks like this: x first dimension, second dimension, 1. So these are the feature map. So from x, you map it into this. Now, with polynomial, you simply need all the cross terms. 1, 2, 1. Okay? This means, this is for second order. This means that you end up with these. You will have one that's x1 square, right? Because of these two. And you have one with this x1, x2. Then you have one with these x1 because of this and this. So all these terms is basically the interaction between every one of them. So that's how you know the feature map for polynomial. Now, this is a pain because polynomial grows really, really fast. So you can end up having like 30, 40, 100 uh, basis functions. And that really complicates things. So I want you to know how to do this. We'll probably do a short one on the exam. But in general, if you have some kind of data, right, you can simply include the polynomial feature and you pass the data in. Now, this is capital. So this is a matrix where each row is your data. If you pass this in, this will give you the phi matrix. All right, so when you're doing a polynomial, this is this is a way to go about it. Like it will make your life a lot easier. Okay, so let's do a quick practice. Right over here, over here. Let's say that we have this one. Right, these are the feature maps. Right, and these right here are two dimensions. So this is just two dimension. And now here's the data where each sample has two dimension. All right, you want to pause the video and see if you can get the phi matrix. Okay, all right, I'm going to move on. Hopefully you were able to get this, right? So this is saying the first dimension is 0, so it'd be 0. And then then this is second dimension square, which is 1, second dimension square. And then first dimension times the second dimension, which is 0. And then the first dimension, second dimension, 1. First, second, 1. So that's how I got this. All right, so now we are currently learning these concept with basis functions, right? We're saying that a function is essentially a combination of basis functions, right? So ultimately, in regression, our goal is to just find this function. Okay. Now, this right now we're using simple ones, but even when we're dealing with really complicated neural network, they're doing exactly the same thing, right? Except, I mean, they're using a very complicated function. So that's the difference. So right now we're learning the basics, but once you know the basics, you can start learning more and more complex functions. And when you have the really complex functions, that's essentially what neural network is when they are doing prediction. Okay. Okay. Oh yes. So yeah, did the neural network? They are also finding this right with a complex function, and they also use gradient descent to solve it. So everything you're learning now like applies to even like very very advanced stuff. So right here, let's say we have a bunch of data, right? And these are two dimension input, right? Over here, I showed you how to calculate W. Okay, showed you how to calculate W. I think I did not append. Yeah, yeah. I should have appended one here. In here, I didn't append it, but you know, it's like for this case, it didn't matter. Okay. And so this right here was this function I showed you. So all you have to do is essentially know, know, no. Well, I use 5, so I probably should change this. This is 5. Yeah, yeah. So yeah, I made a mistake here. It should be phi transpose phi minus 1 phi transpose y. Okay. Uh, so for every x, you want to make sure you use phi. But anyways, this is the correct solution. Now, this is how you perform gradient, how closed form solution, linear regression, or just regression. You can also call linear regression. So instead of I mean, both of them are really just one line. But in Python, sklearn library, you can import linear regression and it will automatically solve it. You just put fit x and y, and then the coefficient is what the weight is. So you can see my solution is almost 1. Their solution is also almost 1. So we basically made similar predictions. Okay. So this is how you solve it, and this is the library you will call. Um, it's both are basically one line. So okay, with polynomial, what you do is essentially you call this fit transform, so that the result is 5 matrix. Once you have the 5 matrix, you can follow that equation that we keep using. Okay, so polynomial, the key once again is for you to just get the 5 matrix. All right, so for the in-class work today, we have, you want to get the data from the website, class website, for the stock prediction. So here I prepare some data for you, and the idea is if you have this bunch of like information from the past month, for example, past month, right, and that could be your data, and then the label is the price change for the next day. So the price change for particular data. So basically, if you know the past month data, and then you want to predict the price change tomorrow. So it could be positive or negative, right? You want to predict the price tomorrow. So this right here, I want you to start off by performing a linear regression. Use the closed form. That's the easiest one to solve it. And once you use it, right, you want to calculate how big your error is. And then just for sanity check, you want to print out your prediction and print out what the actual labels were, just so you can see how closely you track, you predict to the true label. Once you solve it with means closed form solution, you I want you to also use gradient descent. If you can use gradient descent to solve it, they should get exactly the same, right? And then if you can do this, the next is to perform second order polynomial regression. So this is the polynomial. This is the linear. See if you can do it. Again, I did write the code for you if you're really, really stuck, but I really hope you'll be able to do it without extra help. But if you do need help, you're welcome to look at my code and see how I did it. Now, a more realistic data set will be stock prediction. So this is the scale one. And this you want allows you to practice center and scaling. So you might want to center the data and scale them first. So very often, if you're not getting a good prediction, it's because your numbers are not properly scaled. So this exercise will allow you to practice scaling. Okay, so this one is a bit harder to do than this one. Okay, so I think that is the end of the day. Remember to submit your in-class work. Um, I do have extra assignments for those of you that are very ambitious. So this one is predicting blood sugar level from a person. But I think I'm gonna skip that today. So I think that's it. So remember to submit your work. I will see you in the next class.